According to Ecclesiastical Insurance, which specializes in insurance for churches, a church with no lightning protection is about 5 times more likely to suffer structural strike damage than one with lightning protection. That means that you can expect 1 failure in every 5 lightning strikes to a protected church. This isn't surprising given the increasing number of scientific papers that reveal a weakness with code-compliant lightning protection systems. Specifically, a lack of consideration for a mechanism known as space charge shielding. Electric discharges, commonly referred to as corona discharges or St. Elmo's fire, emanating from the lightning rod tip in the minutes and seconds before the arrival of a lightning strike, hinder its ability to intercept the strike when it does arrive. This is a principal cause of lightning protection system failures. Charges in the clouds induce charges of opposite polarity onto the ground, and they're more concentrated at the corners, edges, and peaks of taller structures. When a descending stepped lightning leader approaches, it induces so much charge onto the structures within its field of influence that an upward discharge or upward connecting leader is produced, which rises up and meets the descending leader and completes the connection to ground. But even in the minutes and seconds before the arrival of any descending leader, merely as a result of the movement and buildup of charges in the clouds, in these areas of greater charge concentration, objects in the right location and with the right geometry produce corona discharges. These discharges, which are typically positive due to the typically negative inducing charges in the clouds, pull electrons away from nearby neutral air molecules, producing ions or space charge of opposite polarity to the cloud charge. And, in the same way that the negative charges in the clouds above induce positive charges onto grounded structures, these newly generated positive ions induce negative charges onto objects in their immediate vicinity. This counteracts the effect of the charges in the cloud and suppresses the electric field strength at the lightning rod. So, if, at the moment of arrival of a descending lightning leader, the lightning rod is shielded by its generated space charge, its ability to react will be restricted. Another nearby object with greater exposure to the effects of the cloud charges and the leader charge will launch the upward connecting leader and conduct the strike to ground. There are 2 important factors in determining discharge activity at any location. The space potential, which is a physical quantity determined from the product of the mean ambient electric field and the height, and the corona inception potential, which is an intrinsic quality of an object's geometry and surface conditions. It's the threshold at which the production of electric discharges begins from that object. If the space potential due to the cloud charges that precede a lightning strike at the location where the lightning rod is installed is greater than the corona inception potential of the lightning rod, space charge shielding becomes a threat. Sharp-tipped rods, by virtue of their geometry, have a very low corona inception potential and are highly prone to space charge shielding on almost any structure. Blunt rods are marginally better. The space potential required to produce discharges from a blunt rod could be 10 times greater than that of a sharp rod. However, the space potential at the corner of a tall building or the top of a church steeple could easily be 100 times greater. So blunt rods will perform better than sharp rods, but they're still prone to failures. Elliptically, hemispherically, or spherically shaped lightning rods will have a higher corona inception potential, but only when they're clean and dry. The larger surface area will tend to collect contaminants like raindrops, rain being commonly associated with lightning. It's well known that under the influence of an intense electric field, water drops elongate and act like sharp protrusions that disturb the electric field and severely affect the corona inception potential of an object, making any larger diameter rods, spheres, hemispheres, or ellipsoids about the same as smaller diameter blunt rods. In order to fully address the problem of space-charged shielding, you would need a lightning rod whose corona inception potential is greater than the space potentials which precede lightning strikes, but lower than the leader inception potential, and which is insensitive to the effects of raindrops and other surface contaminants. So far, the only known shape that can accomplish this is that of the Field-Sensitive Air Terminal, or FSAT, by Lightning Electrotechnologies. From a distance, the electric field around the FSAT looks like that of a sphere, and so we can vary the corona inception potential of the air terminal by varying its dimensions. But up close, from the point of view of a water drop or insect on its surface, the electric field is convoluted and complex, and the presence of any raindrops, insects, or other contaminants does not significantly disturb the electric field around the air terminal, and the corona inception potential remains stable, making the FSAT the ideal lightning rod in locations that experience significant space potentials like church steeples, building corners, towers and masts, or just about any structure in a mountainous region. Lightning is perhaps the most complex electrical phenomenon that we face. Therefore, it's unreasonable to assume that protecting against it would be simple, and that there would be no development in lightning rod technology for hundreds of years. The FSAT, it's more attractive.